everyone, welcome to the chapter number 1 solid state of chemistry. In this video we are going to study Schottky defect, Frenkel defect and impurity defect. So let's begin. Let us now study Schottky defect in detail. This defect arises due to missing of equal number of cations and anions from their regular position in the crystal lattice, creating vacancies are called as Schottky defect. In this defect, there is a pair of holes per loss of ion pair are there due to loss of a cation and a loss of an anion. Now, how exactly this is happening? Let us see with this diagram where A plus is a cation and B minus is an anion. Now in this, there is a loss of one cation and loss of anion, and hence a vacancy is developed over there. A paired cation-anion vacancy defect is called as an Schottky defect. As you could see in this diagram also, that there is a loss of a cation and a loss of anion. Hence, this type of defect is called as an Schottky defect. Now, which are the conditions by the Schottky defects are arising? Ionic compounds having following characteristics show Schottky defect. The first characteristics is a compound which has a high degree of ionic character can show Schottky defect. A compound which has high coordination number of anion shows the Schottky defect. As we know, the coordination number is atom which is touching the other atoms, that is whenever it is in contact with the other atoms, and the number of atoms in contact is called as a coordination number. Hence, if the coordination number is high for the anion, then it can show the Schottky defect. When there is a small difference between the size of an cation and an anion, the ratio of R cation by R anion is below unity. Now, due to the Schottky defect, which are the consequences in the crystal lattice? As the number of ions decreases, but the volume remains unchanged, but the density of the substance decreases. As we know that density is directly proportional to the mass. Hence, when a cation is removed or an anion is removed, a vacancy is created and the number of atoms is decreasing. Hence, mass will also decrease. So, the volume will remain same but density will decrease. As the number of cation and anion is equal, the electrical neutrality of the compound is preserved. As we know that one cation is removed, one anion is removed. That is, the equal number of cation is removed and equal number of anion is removed. Hence, the ratio of the cation and anion is same. So, the electrical neutrality for this is preserved. Schottky defect is prominent observed in, for example, sodium chloride, potassium bromide, cesium chloride and silver bromide. Let us now see Frenkel defect in detail. A Frenkel defect is a dislocation defect or a type of a point defect in the crystalline solids named after its discoverer, Yakov Frenkel. This defect arises when ion of an ionic compound is missing from its regular lattice site and occupies interstitial positions between the lattice points. For example, as shown in this diagram, when the cation A and anion B. Now, the cation A from its original position goes in the interstitial site, and hence it develops a vacancy towards the original position, but the cation and ionic ratio remains the same. Similarly, we can observe in this diagram as well. This is a cation interstitial site, whereas a vacancy is developed at the original space. Hence, a vacancy of a cation is developed at the original space. So, at the cation interstitial site, a extra cation is there. Generally, cations occupy the interstitial sites as cations have smaller size than anions. Frenkel defect is considered as a combination of vacancy defect and interstitial defect. As we know that there is a vacancy created for the cation as well, as the cation goes to the interstitial space, hence it is a combination of vacancy and interstitial defect. This creates a vacancy defect at its original position and interstitial defect at its new position. Now, conditions for the formation of the Frenkel defects are: this defect arises in ionic compounds with a large difference in the size of cations and anions. Ionic compounds must have ions with the low coordination number. Now, which are the consequences for the Frenkel defect? The consequences for the Frenkel defect are: since there is no loss of ion from the crystal lattice, the density remains unchanged. As we know that the cation, it is just changing its position. It goes into the interstitial space. So the ions remains the same, hence density will remain unchanged, as well as the electrical neutrality also remains same. This defect is observed in the compounds such as zinc sulfide, AgCl, AgBr and CaF2. For example, we are seeing the crystal lattice for the AgCl. Now in this, Ag is missing, a cation is missing, and it goes into the interstitial space as it is shown in the A diagram also and B diagram also. So this is a type of Frenkel defect. Now let us study impurity defects. What are impurity defects? In impurity defects, the defect arises when the foreign atoms are present in the lattice site in place of host atoms or at the vacant interstitial sites. Now this defect is arising due to the foreign atom, that is some other atom. This is further classified into substitutional defect and interstitial defect. Now let us first see substitutional impurity defect. This defect arises when foreign atoms are present at the lattice site in place of host atom due to their displacement. For example, alloy, that is a brass, alloy of a copper and zinc. In this, brass copper atoms are replaced by the zinc atom. As we could see in this diagram, the blue colored are the copper, whereas orange color is an zinc atom. So here impurity of zinc, it is being substituted in place of copper, and hence this is a type of an substitutional impurity defect. Now let us see the impurity defect, which is a vacancy through a aliovalent compound. Now as we know that there was a replacement of the copper by zinc in the substitutional defect. That is, the oxidation state for the copper was Cu plus 2 and even for zinc was Zn plus 2. Now what is a aliovalent? Whenever there is a replacement of different oxidation state, then the host atom, that is a aliovalent ion. Now for example, in the crystallization of NaCl, little amount of SrCl2 results that Sr2 plus is being there in the sites. Now in this, what happens, Na is having plus 1 oxidation state and Sr is having plus 2 oxidation state, and since it is plus 2, it will replace 2 Na plus ion. It occupies the site of one ion and the other site remains vacant, and hence when it occupies one Na plus, the other site will remain vacant. The cationic vacancies thereby produced are equal number of Sr plus 2. As we can see in this diagram, Sr plus 2 replaces 2 Na plus ion, but one site remains vacant as there is 2 Na plus ions are being replaced in place of 1 Sr2 plus. So this is what it is, a vacancy developed due to the aliovalent ion. Now let us see interstitial impurity defect. Now what is an interstitial impurity defect? In interstitial impurity defect, the impurity of a cation is present in the interstitial position and make crystal defected. For example, stainless steel. The impurity defect found in the stainless steel is interstitial impurity defect. Stainless steel typically contains 1% of a carbon. A carbon is a non-metallic compound and it is much smaller than the iron. The carbon will therefore tend to occupy the interstitial sites in the iron lattice. As we could see in this diagram, the stainless steel, that is the iron, is there, but in the interstitial site a non-metal which is a carbon is there. So this type of an defect is an interstitial impurity defect. So thank